Hello everyone, this is Sahana Kulkarni. Again, today we are going to discuss the continued part of the chapter moving charges and magnetism in this session 5th. So in this case, first we will discuss regarding what is Ampere's circuital law. So the statement of the Ampere's circuital law is the line integral, that is the line integral B dot dl for a closed curve enclosing an area which is equal to the mu naught times the net current which is flowing through that area bounded by the curve. So the line integral means overall entire closed curve we have to consider. The line integral for B dot dl for the closed curve, that must be equal to the mu naught times the net current which is flowing through the entire bounded area of that curve. So therefore that we can write it as it is the line integral B dot dl, that must be equal to the mu naught times the current I, that is mu naught into I. In the equation form, just you remember the Ampere circuital law, that is the closed integral. So this is the special integral that you are observing here, the integration with a circular loop, that is nothing but it is integration for entire closed curve. So that B dl is equal to mu naught into I, where B is the magnetic field due to the current I, and the closed curve or the loop, that is called as the Amperean loop. Here that entire closed loop we can call it as it is an Amperean loop. So this is the statement of the Ampere circuital law, that is the line integral B dot dl for a closed curve or a closed loop which is enclosing the area, that must be equal to the mu naught times the net current which is flowing through that entire area or the bounded curve. Next, we will discuss what is the magnetic field due to the straight conductor of infinite length which is carrying current. So for that we have to consider one infinite straight conductor. So consider a straight conductor of infinite length in the plane of a paper. Let I be the current which is flowing through the conductor in the form x to y direction or from x to y, and let P be a point which is at a distance r from the straight wire. Now we have to consider one circle of radius r which is passes through the point P to get that an Amperean loop. One closed curve or one closed loop we have to get at certain point P, that we have taken it as a circular loop. So see here we have taken one straight conductor of infinite length and the current I which is flowing from x to y direction, and P be a point which is at a distance r from the straight wire. Then we have to consider a circle of radius r which is passing through the point P, and that is called as an Amperean loop. Then the magnetic field B at a point P due to the current which is flowing in the wire and which is along the tangent to the circle. So the magnetic field B which is acting because of the current which is flowing through the conductor, that is straight infinite long conductor, and that will be nothing but it is a tangent to that circle. Therefore the magnetic field B which is parallel to the current element, or you can say the line element, that is dl at a point P. Then we have to apply the Ampere circuital law to the circular loop of radius r. Therefore the line integral B dot dl is equal to mu naught times the current I. Mu naught times the current I we are getting, that is our Ampere circuital law, that is B dot dl is equal to mu naught times the current I, that is mu naught into I. Now but here line integral B dot dl, that must be equal to, we can write it as it is B dl cos theta. So here theta is equal to 0 because our magnetic field B which is parallel to the dl means both are traveling in a same direction. Therefore angle itself is equal to 0, both are parallel means angle theta is equal to 0. Therefore B dl cos 0 we have substituted, cos 0 is 1, Therefore, we are getting it as B into, B is a constant in entire circular loop, into the the line integral dl, and this line integral dl that will be continued for the entire circular loop. Therefore, B into, we are taking that dl is equal to 2 pi r. Therefore, we have to substitute that B into dl is equal to, it is B into 2 pi r, that must be equal to mu naught times the current I. From this, B is equal to, we are getting it as mu naught I divided by 2 pi r, or the same equation we can write it as it is mu naught by 4 pi into 2I by r. So this is what from this result we have the following points, that is the magnitude of the magnetic field at every point on the circle of radius r, that is same, means the whatever the ampere and loop you are getting of certain radius, the entire magnetic field that will be remain same at that entire radius, it is not going to change. The direction of magnetic field at every point on the circle, it is tangent to it. The direction of magnetic field, that is every point on the circle, it is tangent, or you can say the parallel to the dl term. The lines of constant magnitude of magnetic field, they form the concentric lines, and these lines are called as magnetic field lines, and they will form a closed loop without any starting or ending point. So this is the only difference between the properties of electric field lines and the magnetic field lines. So electric field lines, they do not form a closed loop, but the magnetic field lines here, they will form a closed loop without any starting and the ending points. And similarly, even though the wire carrying current is of infinite length, the magnetic field at non-zero distance is not infinite. So whatever may be the current carrying conductor, it is of infinite length, but the magnetic field at a non-zero distance is not at all infinite, since we can say that B is inversely proportional to R. The magnetic field B goes on decreases as the R goes on increases. Next, we will discuss regarding the one more concept, that is a solenoid. Solenoid is nothing but it is consists of a long insulated wire which is wounded in the form of a helix, where the neighboring turns are very closely spaced with each other. When a current which is flowing through the solenoid, the net magnetic field that will be given by the vector sum of the fields due to the each turn or all the turns. And inside the solenoid, the magnetic field is very strong, and outside that it will be 0, or it will be going to be V, and which is parallel. Inside the solenoid, the magnetic field is strong and also which is parallel, and outside the magnetic field goes on weak. And for an ideal solenoid, the magnetic field at the outer side of the solenoid is 0. So whenever you are considering the ideal solenoid, the magnetic field at the outer side, it will be completely 0. It is not going to weak, it is completely 0 itself. So solenoid means it is one long insulated wire which is wounded in the form of a helix, and the neighboring turns, they are very closely spaced with one another. Then when a current which flows through the solenoid, the net magnetic field will be given by, it is the vector sum of all the fields due to the individual terms or individual turns. So inside the solenoid, the magnetic field is very strong and it is a parallel, and outside the magnetic field is weak. And general ideal solenoid, if you are considered, the magnetic field outer the solenoid is 0. So coming towards the derivation of that, so for that, the step 1 we have taken, let P be a point which is well inside the solenoid, and we have to consider one rectangular loop, that is ABCD, that is known as an Amperian loop. When that point P which is passes through that, already you are observing in the figure, just point P is below here, that point P which is enclosed by that rectangular loop. Then the line integral B dot dl, the magnetic field across the loop, that will be given by, that across the ABCD, that will be given by the line integral ABCD, that is for B dot dl. That will be given by the line integral B dot dl for AB plus the line integral B dot dl for BC and the line integral B dot dl for CD as well as line integral B dot dl for AD. Just to observe here, that is magnetic field inside the solenoid, it is always acting parallel. Just to observe the B lines, that is parallel. Therefore, the BC and AD, they are acting perpendicular here. So that is our next point. B is perpendicular to BC as well as DA. So once it is perpendicular means the line integral B dot dl for BC, that must be equal to the line integral B dot dl for DA or AD, that is equal to line integral B dl cos theta. So both are perpendicular means cos theta becomes 90, cos 90 is 0. Therefore, the line integral for BC as well as DA, we are getting it as 0. So only the parallel terms are left out. Since path CD as well as AB, they are parallel to the magnetic field. So once they are parallel to magnetic field means theta equal to 0. So cos 0 is 1. Yes, of course, there will be the magnetic field acting over there. But CD, which is the point which is lying outside the solenoid, and here we have considered the ideal solenoid. For ideal solenoid, outside the solenoid the magnetic field becomes 0. Therefore, for CD, the outside the solenoid the magnetic field which is acts on it, since path CD and AB, they are parallel to the magnetic field and CD is the outside, so there will be no magnetic field acts on that. Therefore, the CD, that B dot dl is equal to 0. Only the magnetic field will be acting for the path AB. Therefore, for path AB, theta is equal to 0 we have considered. Therefore, line integral B dot dl for AB term, so that is equal to B dl cos theta for AB. Therefore, dl, it is parallel means theta is equal to 0. Therefore, we got it as it is B dl, and B is constant everywhere. Only the line integral is applicable for dl. Therefore, all these dl terms, whenever we are going to integrate for all the AB, that you are getting it as capital L. Therefore, we got it as line integral B dot dl is equal to BL. So this is our second equation. Next, we have to compare the general equation with this equation with the general equation, that is Ampere circuital law. So according to Ampere circuital law, line integral B dot dl must be equal to mu naught times the net current which is enclosed by the loop ABCD. Therefore, equal to mu naught into the net current is nothing but the number of turns in the loop in the ABCD into that I. That we can write it as B dot dl is equal to mu naught, the number of turns is L, consider the length L also, N into L into I. So this is the third equation. So we have to compare both the equations, that is line integral B dot dl is equal to, that already we have done with the second equation, that is BL is equal to mu naught N L I. So L get cancels, we are getting B is equal to mu naught N I. So this is the magnetic field which is well inside the long solenoid. Next, we are going to discuss regarding the toroid. Just to observe both the diagrams of the toroid here. A toroid, it is nothing but a circular ring of finite thickness on which a large number of turns of insulated wire, they are closely wounded. Solenoid and toroid both are same, but in solenoid, which is in the form of a long helical shaped form, but in toroid we are getting it in the form of a circular shape. A toroid, it is a circular ring of finite thickness on which a large number of turns of insulated wire, they are closely wound. So now we have to consider a toroid which is having n turns per unit length. Then let I be the current which is flowing through the toroid. Then magnetic field lines are form a concentric circles of radius r. Then we can write it as the line integral B dot dl is equal to B dl cos theta. So B is acting tangent to the path dl, both are parallel, therefore theta is equal to 0. Then we are getting B dot dl, that is equal to B dl cos 0. Cos 0 is 1, therefore B into line integral dl, that we can write it as B into dl is nothing but it is a circumference of the circle of radius r. Therefore, B dot dl is equal to B into 2 pi r. I will write it as it is equation number 1. Then according to the Ampere circuital law, line integral B dot dl is equal to mu naught into net current which is enclosed by the circle of radius r. That will be given by mu naught into net current, which is nothing but it is total number of turns into I. Therefore, B dot dl is equal to mu naught, n number of turns are there and each are having covering 2 pi r length, that is 2 pi r into I. So we have to compare equation 1 and 2, that is B into 2 pi r is equal to mu naught n into 2 pi r into I. So 2 pi r get cancels. We are getting B is equal to mu naught n I. So this is what the magnetic field which is due to the toroid carrying current. So just go through both of the solenoid as well as toroid.